As part of a bonus, I'll be putting a little bit of what we call logarithmic differentiation on your next test. If you choose not to do it, that's totally fine, but there'll be about 3 points of extra credit, test extra credit for the process. So I'm going to creep up on it here and talk about these. If we're doing this in class, I'd have you do it, obviously, but we're going to go bonus with this year. E is a constant, and e to any constant is still a constant. Derivative of all constants are zeros, so nothing goofy going on that one. The derivative of e to the u is e to the u times du dx. So the derivative of e to the x is e to the x, but the reason for that comes from what we call logarithmic differentiation. So that you know because it's memorized, but I never proved it to you. The derivative of x to any power is the power rule, and e is a power. So this would be, bring the power out front, drop it down 1. So totally not new, totally not new, not new, but we just memorized it. And then this last one is a big question mark. So I'm going to go to the last one before I go back and prove this guy right here. So what we do a lot of the times, almost always in math, when we have the variable in the exponent, is we use the property of natural logs that say that you can bring the power out front. Now that can be proven too, but I can only go so deep in this. Hopefully somebody proved it to you in Algebra 2 or pre-calc or something. So watch what I'm going to do. I'm going to let y equal x to the x. And I'm looking for y prime, or dy dx. What is it? I don't know. So the first thing we'll do is take the natural log, this is why it's called logarithmic, of both sides. Totally legal to do the same thing to both sides of the equation. And then we'll use our property of natural logs that says the powers can come out front, and we'll now have what is a product. We know how to take the derivative of products. We use the product rule. So what I'll do now is basically implicit. I'm going to take the derivative of both sides with respect to the independent variable. Normally you won't show that step, but it's the first one, so I'm showing everything. What's the derivative of the natural log? It's 1 over u times du dx, or times the derivative of the guts, which in this case is the derivative of y with respect to x. It's dy dx, also known as y prime. On this side, I'll use the product rule, and it's all with respect to x, so it's just first, d second, plus second, d first is 1. Remember, I'm trying to figure out what is y prime. So what is y prime? If I just multiplied both sides by y, I'd have it. So my y prime, also known as dy dx, or the derivative of y, is equal to 1 plus the natural log of x times y. Right? I'm multiplying both sides by y, and my y was x to the x. So that is the derivative of x to the x. Kind of complicated. College Board does not test that. Should they? I don't know. So now I said I was going to prove this guy to you. Why is the derivative of e to the x e to the x? Well, let's do this one similarly. Let's let y equal e to the x. Let's take advantage of our natural log properties to natural log both sides, which allows us to bring that exponent out front. The natural log of e is 1. So now I have the natural log of y is equal to x. I know how to take the derivative of the natural log of y, and I know how to take the derivative of the natural log of x. So the derivative of the natural log of u is 1 over u times du dx. In this case, it'd be dy dx, or in this case, it would be y prime. That's this, derivative of the natural log of y. The derivative of x dx, or dx dx, is 1. When I multiply both sides by y, and y is really e to the x, you'll notice I get e to the x. So that's why the derivative of e to the x is e to the x. So let's go down to this guy, and let's see what happens here. Find the derivative of, I don't want to do x to the 2x because it's too similar to x to the x. I think we should do x to the sine x. I think that sounds more fun. So bam, 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 bam. All right, y equals x to the sine x. Actually, I'll still need that on there because we can't natural log negatives. All right, so first thing I'll do, and again, I'm in search of y prime, but I'm going to take the natural log. It allows me to bring the power out front, a la pre-calculus and algebra 2. Next, I'll take the derivative of both sides. I'm just going to write it out here. I'll put it all the way over there so you can see I'm taking the derivative with respect to x of everything. The derivative of natural log is, again, 1 over u times u prime. So in this case, 1 over y times y prime. On this side, I have the product rule because I have the product of two functions. So I will do first d second plus second d first. And the derivative of sine is cosine. So let me travel on through here. The derivative of sine is cosine. Now I want to get rid of the y, so I'll multiply both sides by y. That'll leave me with just the derivative, which is what I'm supposed to find. It said find the derivative of y, which means find y prime. It equals sine x over x plus ln x cosine x, all of it times y. But y was, again, this problem has to be in terms of x. Y was x to the sine of x. What do you think about that? It's not particularly difficult, right? So let's go to the next page. In one of your sets of notes, I said you really just need to memorize this. The derivative of e to the x is e to the x, but technically in the proof there was an ln e that went to 1. I just showed you that. Well, the derivative of 2 to the x is the same thing. It is 2 to the x, but there's an ln 2 hanging out front. Watch, when it says, watch me show you this so you don't have to memorize a formula that says the derivative of a to the x is ln a times a to the x. I could just say, suppose I forgot. All right, so my y is 2 to the x. I see that variable in the exponent and I say, hey, let's natural log both sides so it can come out front. I now know how to take the derivative of both sides. The derivative of the natural log of y is y prime over y. The derivative of the natural log of x is x prime over x. The derivative of the natural log of u is u prime over u. All right, so back over here, the derivative on this side, this is a constant. It's like me saying, what's the derivative of 5x with respect to x? And you'd say 5. What's the derivative of 8x with respect to x? It's 8. What's the derivative of the natural log of x with respect to x? Sorry, natural log of 2. X with respect to x, it's the natural log of 2. It is the constant. It's a number. Natural log of 2 is a number. So I have ln 2 here, score, and then I'll have to multiply by y, which is really 2 to the x. So you see, I don't really need to memorize things if I know where they come from. So when we did this in class, I said, you know, we're not going to prove it for you this year, but some of you should be able to understand that. So this last one up is a little different. So this is kind of a different train of thought, but it says find the derivative using logarithmic differentiation. What that means is using the property of logarithms. Up here, I was using the fact that I could bring an exponent out front and that variable was stuck in an exponent. In example 7, the variable is not stuck in an exponent, but I still have some properties that if I took the natural log properties and applied them, I'm not going to take the natural log of both sides because I don't need to bring a variable out front to get it out of the exponent. But I do know from pre-calculus that division expands into, right? So here, for this guy, let's do this. The natural log of y is going to equal the natural log of all of this stuff. I'm going to write it all out. I'm trying to save some space here, but, and we like to see power, so I'm going to write x squared plus 1 to the 1/2 down here. All right. What that means is I can take this division and go subtraction. So that's one of the properties. Division expands into subtraction. Furthermore, I can bring the power out front. That looks like it's lofted. Let's put it down here. So division goes to subtraction. And the powers, so instead of writing to the 1/2 right here while I'm at it, I'm just going to go over here. That's what the natural log of y is. However, I don't want to know what the natural log of y is. I have it. I want to know what y prime is. But now it's in a form where I can take the derivative of everything with respect to x. And over here on the left, again, I get y prime over y, u prime over u, x prime over x, where x prime is 1. It's always the same thing. Over here, I'd have 2 constant multiple rule. The derivative of u, or u prime, is 1 over u, minus 1/2 of the derivative of u, or u prime, over u. So now what I would do is multiply the whole thing through by y. What was y? It was x minus 2 quantity squared over the square root of x squared plus 1. And you know, I can do some cleanup in here with some canceling. If I had to, I could get a common denominator. But for the most part, the calculus is done. So again, what we did is we're using, I'm going to do one more, I think. That's going to have a 15-minute video. Suppose it was x plus 3 to the 4th power all over the square root of 4x minus 1. And let's make it 4, yeah, that's good, 4x minus 1. Doing this with the quotient rule would be really ugly. Wouldn't you agree? Like, that's super ugly to do with the quotient rule. But if I use my properties of natural log and say, well, natural log allows me a logarithmic differentiation because I'm using it to help me because I know the derivative of this, and when I expand this out, it makes it so much easier. So I'll have the natural log of y is equal to the division, again, expands into subtraction. And I actually realize that it's the natural log of all of that stuff. So it'd be the natural log of x plus 3. The minute I'm about to write to the 4th power, I'm going to use that property of natural logs to bring it out front. Minus the natural log of 4x minus 1 to the 1/2 power, but powers come out front of natural logs. So over here now, I have not taken a derivative. I natural logged both sides, and it allowed me to expand that side out. Didn't you ever wonder, why do you learn how to expand logarithms? Like, when would I ever use that? Well, it's an aid in taking a derivative, because now it took something that with the quotient rule would take me forever. Like, it'd be low D high is chain minus high D low is chain, draw a line square. It'd be such a mess. It could be done though. But now I just say the derivative of y, natural log of y is y prime over y. Constant multiple rule, u prime over u. Constant multiple rule, u prime over u, right? Now, I could clean that up like this. Just take half the 4 and put a 2 here, right? Maybe put the 4 nicer on the top. Basically, that's what y prime over y is, but I only want to know y prime. So I go like this, and I go like that, and I go times x plus 3 quantity to the 4th over the square root of 4x minus 1. So logarithms as an aid in taking a derivative. I will put one of them on your next test as a bonus.